Hi, my name is Tal, and this talk is about a stronger bound for linear 3 locally correctable codes. Locally decodable and correctable codes are defined as follows. So we say that C a code over, let's say, the binary alphabet for simplicity is a Q delta LDC or a Q delta locally correctable code if there exists a randomized procedure which gets access to Z, which is a noisy version of a code word, and it needs to always make at most Q queries to Z, the noisy code word, and if Z is a distance at most delta n from some code word, then the requirement in the case of LDC is that A outputs a bit of the message with a high enough probability. And in the case of LCC, it should output a bit of the code word with high enough probability. So it should be true in the case of LCC for every I between 1 and k, in the case of LCC for every j between 1 and n, and index within the code word. These are very important types of codes, of objects. There are examples for them. I listed some of them. The Hadamard code, for example, is a 2-query locally decodable code and 2-query locally correctable code of exponential size. Sometimes I'll just say QLDC or QLCC, and I mean by that is that delta is any constant. So locally decodable codes were first defined by Katz and Trevisan in 2000, formally defined. They have LDC and LCCs have applications in very important areas. I want to say that locally correctable codes, they are stronger objects than locally decodable codes. It's easy to see that in the case of linear codes because we can just assume that the encoding is systematic. In the case of 2-query locally decodable code, in fact, Goldreich, Karloff, Schulman, and Trevisan showed the following. They showed essentially that the Hadamard code is essentially optimal because they show that any linear 2-query locally decodable code, k, the message length or dimension, is at most logarithmic in the message length. What about, so this sort of, so at least in the case of 2 queries, we sort of have our answer. What about more than 2 queries? So I want to mention some polynomial bounds that are known for Q-query locally decodable codes. So Katz and Trevisan showed this bound. In this talk, we are going to assume that Q is constant. So this is a polynomial bound. Just to get a feeling of this bound, take, for example, what it gives when Q is 3 LDCs. By the way, it also bounds 3 LCCs because we said that LCCs are stronger than LCCs. So we get that n is at least k to the 1.5. Kernadis and de Wolf improved this bound in 04 by showing this. There is 2 cases, if the number of squares is even or if it is odd. So again, to get a feeling, in the case that Q is equal to 3, we get here that n is omega tilde of k squared. So for a long time, this was what was known in the general case for Q LDCs, for Q larger than 2. And then in 22, there was really a great breakthrough by El Rabia, Goswami, Kothari, and Manuar, which were able to show that in the case of 3-query locally decodable code, n is at least omega tilde shel k cubed. So this was a very important improvement. And near the end of last year, in a surprising and fantastic development, Kothari and Manuar were able to show this. They show that for linear 3-query locally correctable codes, in fact, the message length n must be at least 2 to the omega of k to the 1/8. So a very strong bound. So in fact, this bound is not even true for LDCs. And I want to remark that they also showed that these bounds hold not only in the binary case, but also for alphabets that are of size, for any alphabet that is of constant size, that is because these are linear codes, then for every field of constant size, this holds. And read-Muller codes, they yield three-query locally correctable codes with this length, n to the order of k, square root k. So after their bound, the answer was somewhere between 1/2 and 1/8 for the power of the k in the exponent. So now I want to state the result that I'm presenting. It's very easy to state. We just improve the 1/8 to 1/4. So we get a bound that is, we got a bound that is closer to the upper bound by Reed-Muller. And so this bound also holds in the non-binary case. And another thing that we prove is that in the specific case of design three-query linear locally correctable codes, n is at least 2 to the k to the 1/3. So I don't want to say formally what are design locally correctable codes. It is enough, I think, to say that Reed-Muller codes, they fall into this subclass, important subclass of locally correctable codes. So in the case of design three-query locally correctable codes, after our work, the answer was somewhere between 1/2 and 1/3. Okay, so now I want to mention subsequent progress that was made after our result was published. So there are some exciting developments. Al-Rabia and Goswami, they were able to show an almost tight bound, almost k to the squared. We have this log k factor. So their bound is for every linear binary three-query locally correctable codes. And their bound builds on a breakthrough in something called rainbow cycles, so a breakthrough in combinatorics, a recent breakthrough by Alon, Buchik, Sauerman, Zakharov, and Zamir. And also another cool thing, very cool thing in the result is that they give implications for improvements in the polynomial bounds for Q LCCs for odd Q larger than 5. So it was great and a beautiful proof. Okay, and also Kotari and Manua had two more results, two more flavors of results in another paper. They showed that for every linear binary, let me call it perfect design three-query locally correctable code, because there is some subtlety. It's not exactly design 3 LCCs. It's another subclass, sort of means that the design or something needs to be perfect about it, but Reed-Muller does satisfy this assumption as well, and this is an important subclass, very important subclass. So they are able to show that in this case, even more tight bound, up to this 1 minus little o of 1. And they also got a results for nonlinear smooth three-query locally correctable code. So up until now, all results were for linear codes. So they also were able to show to get better bounds in the case of nonlinear smooth codes. So the smooth here, it's assumes something on the behavior of the decoder. So in the case of smooth codes, the bound that you get depends on the completeness of the decoding procedure. So for example, if the decoding procedure always succeeds or almost always succeeds, then the bound that in their work is n to the k to the omega of log k, which is super polynomial. Okay. So after presenting this very important progress that they made, I want to give a taste of the proof of the bound that I stated, the 1/4 and the 1/3 in the case of designs. And I'm actually going to, so I'm not able to show the entire proof because of time constraints. So I do want to give some tastes, but let's only do it for the case of designs, which is more simple, so the 1/3. And just going to be a taste. So first, let me talk about the approach. The proof is in the Kotari manual framework. So Al-Rabia, Goswami, and Manuel in their bound for 3-query LDCs, and also Kotari and Manuel for in the exponential bound for 3 LCCs. Both of these works make use of the Kikuchi matrix method or the spectral refutation method. So in these works, one assumes for contradiction that the code length is small and gets to a contradiction, and the contradiction comes from analyzing the spectral norm of a Kikuchi matrix. So by bounding the spectral norm, you get a contradiction. You show that it cannot be that many of a set of equations is satisfied. So you get a contradiction without getting too much into it. So the proof of our bounds here doesn't use spectral refutation. We don't analyze the spectral norm of a matrix. What we are going to need, we are going to reduce to the case of 2-query locally decodable code, a combinatorial reduction. And actually, this part of reducing to 2-query locally decodable code also is also part of the works of Al-Rabia, Goswami, Kotari, and Manuel on 3 LDCs, and also that of Kotari and Manuel for 3 LCCs. They also have a part where they reduce to 2 LDCs. And actually, also the Fernandez and the Wolf bound for that improve upon the Katz-Revitsan bound also makes a reduction to 2-query LDCs, and there are similarities between these reductions. So Kotari and Manuel extended the Kikuchi matrix method in the case of 3 LCCs by using these bright new ideas. So one idea that they have is they use this idea of long chain derivations. So we are going to have something equivalent to that, to their idea of long chain derivations. And also they have this something called, they call continuously regular partitions, which is something that they do in order to handle some problem that arises. So we are also going to have in our proof something that is similar to what they do there in the continuously regular partitions. Of course, there are some differences, but both of these very bright ideas, we have things that are equivalent to what they did there. So as we said, the proof plan, like in other works, is to reduce to 2 LDCs. So we are going to start assuming some 3-query locally correctable code. And let's assume without loss of generality that the code is systematic. And the goal is to construct some code C prime, which is a 2-query locally decodable code of length capital N. And hopefully, capital N is not going to be much larger than N. And then we will be able to conclude that N must have been large to begin with, because we know that 2 LDCs must have exponential size from the Goldreich et al. Bound. So now I want to state a structural lemma. And the definition of LCCs or LDCs sort of how to work it as is, because it's more in the form of a story that there is some procedure that does such and such. So we need something more structured in order to be able to show claims. So let me attribute the following lemma to Katz and Trevisan, even though they prove something that is similar in spirit, but not exactly this. So assume that you have a code which is a linear QLCC or a QLDC. So what does it mean? It means the following. It means that for every coordinate j in n, there must exist a set of sets where each small set is a subset of the coordinates of size at most q. This satisfies the equation that we see here. The equation means that if you want to get the j's coordinate, you can do it just by summing up the coordinates that consist this small set. So for every coordinate, there must exist this set of subsets of the coordinates of size at most q. And we also have that these subsets are disjoint from each other, and the number of them is large, omega of n. So, and in the case of locally decodable code, it's similar, just the subsets of size at most q give us a way to get x at location j rather than cx at location x at location I rather than cx at location j. And I want to say that the other direction is also true. What do I mean by that? Let me say it for QLDCs because we are going to use it. If one wants to show that a code is a QLDC, it's enough to show that there exists these sets of subsets of the coordinates, that for every index I in K, there exists such a set of subsets of the coordinates of size at most q, that by summing up these coordinates, you get x at location I, and they are disjoint from each other, and for every I, they are omega of n such. So usually we call them Q matching, these sets that correspond to some I, because they are matching within a hypergraph. Okay. So now we want to say we are going, in order to get an exponential bound, and this is the equivalent of the Kothari-Manuar idea that they call long chain derivation. So the decoding sets, we do have them. If you have a three-query locally correctable code, then you have omega of n decoding sets for every bit of the code word, for every coordinate of the code word. So, but the problem is that there is only omega of n such, and it is not enough to get the bound. So we want to generate more of them. So we are going to see a way to do it. But first, let's more formally say that let's call them the sets from the Katz-Revison lemma. Let's call them decoding sets. So a decoding set is just of a coordinate j is just a set of three queries or three coordinates that can be used to decode cx at location j by summing up these coordinates. So again, they are disjoint from each other for m and j, and there is omega of n of them. So let's use this notation. We give them names. Let's call them aj alpha, bj alpha, cj alpha, and j is the coordinate that we want to decode, and alpha sort of means the randomness, because there are m sets, so alpha says which one of them, and let's also call alpha R1 for reasons that will be clear now. Okay, so we are going to generalize this to a decoding sequence. A decoding sequence, the way that you generate a decoding sequence is, again, you have some coordinate that we want to decode, some j, and instead of getting just one alpha or just R1, now we get S elements within M. So like a randomness of length S. And the way that we use the instructions is in the following way. We use R1 to choose the first triplet, that the first decoding set that decodes the j coordinates. So here I draw it down. And now what do we do with R2? Instead of using CJR1 inside our triplet, we are going to remove it and decode it. So we are just going to take the R2 decoding set of CJR1. And now we have 5 coordinates. It's easy to see that they still give us the J's coordinate, these 5 coordinates. So, and we do so further with the C coordinate of this triplet that we added. And now we use the third instruction R3 and so on. And we do it S times. So eventually we got an odd number of coordinates that give us a way to decode Cx at location J. Okay, so here we have like a formal definition, but what I want to say is that eventually we take all of the A elements that we had, and we call them the A part. This is a sequence or a string. We take all of the B elements and we call them the B part. And we also take the C, the last extra coordinate that we had, just a single coordinate, and we call it the remainder or the C part. So the A part, the B part, and the remainder of the decoding sequence. Okay. So the useful property that we maintained is that all of these coordinates together can still be used in order to get Cx at location G. So let's call it the useful property. So how do we get to a 2 LDC? So let's define something called the asymmetric graph. For every index of a coordinate J, we are going to define the following bipartite colored graph Gj. With this set of left vertices and this set of right vertices. So the left vertices are just all subsets of the coordinates, all the ways to choose exactly S subsets of, always to choose S subset of the coordinates of size exactly L, and also one extra coordinate. And the right vertices are always to choose S subsets of the coordinates of size exactly L. So here we have two examples. A left vertex has S subset of the coordinates, each one of size L, and the extra coordinate, and a right vertex just a subset of the coordinates of size exactly L. So the colors are going to be colors of the edges, not of the vertices. And the colors are in fact going to be all of the possible instructions. There are m to the s possible instructions that correspond to the decoding sequences. So we put an edge of color R between two vertices LH and L prime from the left side to the right side. If the following holds, we consider the R's decoding sequence coming out from J, and we check if A is contained within L, and L is a sequence of subsets of size L. So what does this mean? It means that we require that the first element of the A part of the decoding sequence should be a member of L1, the second element of the A part should be a member of L2, and so on, until the S element of the A part should be a member of LS. We also require that the H part of the left vertex should be equal exactly to the remainder of the decoding sequence. And from the other side, we require that L prime should be equal to exactly what you get if you take out the A part and you add the B part. What does this mean? It means that, for example, in L1, we take out the first element of the A part of the decoding sequence, and instead of it, we add the first element of the B part of the decoding sequence. And we do this for all of the S elements. Okay, so we have more edges, each one for every R, for every set of instructions, or for every decoding sequence, we have a set of edges with these colors. So we want to get 2LDC C prime. So we are going to define a code on top of the vertices. For every vertex, we are going to have a coordinate of C prime. So the left vertices just correspond to summing up all of the coordinates that appear in all of the subsets of Cx, and also the extra coordinate H, and the right coordinates correspond to right vertices are just summing up all of the coordinates that appear in these sets. So what is useful about this graph? So following from the useful property of decoding sequences, we know that for every edge LH, L prime in the graph Gj, if we sum up the two coordinates that correspond to the two vertices of the edge, we exactly get Cx at location J. So notice the subtlety here. Here it's Cx at location J, and here are coordinates of C prime. And this is sort of the thing is we start from a 3 LCC and we get a 2 LDC and not a 2 LCC. So the reason that we do get CX at location J is that what happens is all of the elements besides the decoding sequence get cancelled out, because L1 and L prime have some common coordinates, and the common coordinates get cancelled out, and the only thing that is not common is the first element of the A part and the first element of the B part, and so on for the other subsets. And eventually, together with the extra coordinate, which is exactly equal to CJR, we exactly get all of the elements of the decoding sequence, and therefore CX at location J. Okay, so so we said from the other direction of the lemma that we want to, in order to show that the code is a 2 LDC, it is enough to show that there is a large matching for every index of within the message that we want to decode. But can we argue for a large matching in GJ? And large, we mean omega of the number of vertices or the number of coordinates here? Of course not, because this graph is asymmetric and unbalanced by a factor of n. So no hope, and this really matters. So no, we cannot. So in fact, there is a trick that we can do. We are just going to make the graph balanced by duplicating each right vertex enough times, exactly n times. And now the graph is exactly equal. On the left side and the right side, there is the same number of vertices. Just duplicating, not changing the meaning or the definition of the coordinates in C prime, just duplicating some vertices. So it turns out that in this case, if we choose the parameters S to be roughly log n and L to be roughly log n, then yes, there is a large matching in this graph. And this means that our code C prime that we defined, which again gives you CX at location J by summing up the two ends of an edge, the two coordinates correspond to an edge. So it turns out that it does, so this means that this code has a large matching for every J. So we assume that our code is systematic, so in particular for every J in K, there is a large matching decoding CX at location J, which is exactly equal to X at location J. So it follows that C prime is a 2 LDC. And now we can use the bound for linear 2 LDCs because it's linear, that K is order of log n, where n is capital log capital N. So capital N is exactly because the two sides are of equal size. So it is log of 2 times n choose L to the power of S times n, which is equal to order of SL times log n. And we get log n to the power of 3 in the design case. So I do want to say that showing this, that there is a large matching, it takes a careful, delicate analysis, which I'm not able to show at all. And also in the general non-design case, the analysis is more complicated, and also the graph itself, the asymmetric decoding graph, is also more complicated. It is not as simple as it. So this is what we proved, the bound. For open questions, any improvements, so the next case to handle is Q equal 4. Any improvement here over the polynomial bound from Canadis and de Wolf would be really great. And also there are some questions regarding the alphabet. So even after the Al-Rabia Goswami almost tight bound for 3 LCCs, so in the case of fields that are not of characteristic 2, for example, F3, we don't know their bound to hold. So in the case of F3, for example, this bound of K to the 1/4 is still what we know. So any tighter bound here or for other fields would be great. And also the case of larger alphabets, this bound and the Koutari-Manuel bound, they don't work for large alphabets. So any bound for large alphabets, will be nice, very nice. Thank you.